right. Welcome everybody to today's webinar. We'll be talking about optimizing tooling and molding and how best to do maintenance and management of those. With me today, I have John Martinez from RFID Inc. John's been involved in the RFID industry for 23 years and a member of RFID Inc. since 1999. Prior to his working with RFID technologies, he was involved with the microcomputer industry. In the late 1990s, he observed the progression from PC-based operating systems moving to chip-level storage. And like Moore's Law, he saw the decline of yesterday's technology with the improvements for tomorrow. And my name is Tim Stewart. I'm with Visual Decisions, and we have been working on basically combining the smart factory and the lean factory since about 2002. And we're excited to have John with us here today to talk about how we can optimize tooling and molding. In addition, we have John's colleague, James Sherrick, and also Rob Simmons from we have Rob Simmons here with us today also. All right, thank you very much. And with that, I'll get started by handing it off to John.
Hi, good morning, everyone. I want to thank you for your participation this morning. Today, what we'd like to talk about is some examples on how RFID applications are applied to various molds in tools for verification and whatever that automated process might be. So we'll delve into that a little bit with, let's see if I can scroll to the next slide here. We're going to talk about molds for mannequin identification and manufacturing, the molds and tools for manufacturing in razors, engine blocks, exhaust pipe bending, and CNC operations.
Sorry, John, there you go.
Okay. The first thing we want to talk about are various tag technologies that are utilized. And one of the things that we find is that all of these are what's called passive tag technology, where the tag doesn't have any energy except that is provided from the radio waves from the antenna. So these are all passive tags. Typically, you look at short read distances for all of these applications. Though recently we found that using ultra high frequency, the 865 to 928 bandwidth, that we're able to get extended distances. And we'll talk about each one of those and how they apply to each one of these applications that we just discussed earlier. Now I have to poke over here to keep scrolling down. Low frequency is typically plug and play, short read distances, very precise reading. You're only reading one tag at a time at a very short read distance. 13.56 megahertz, it initially allowed for greater storage, but it's not as metal friendly. So a lot of these applications for tool and die and mold identification aren't very well received with 13.56 megahertz. And typically you won't be able to apply a 13.56 megahertz tag embedded into a metal substance. (915 megahertz is the ultra high frequency that we discussed earlier. This gives us read distances from a short read range for very precise to up to 10 meters in some cases, depending upon the size of the tag that's being utilized, as well as the gain of the antenna and the orientation of the tag to the field of the antenna. The other thing that UHF offers is the ability of reading multiple tags at one time. Well, this is referred to as anti-collision. Excuse me. I want to talk about various applications that were mentioned in the first slide. The first thing they want to show you is the mannequins and how this was related for both a safety feature as well as a productivity benefit. So in this case, we had a company that came to us that manufactures mannequins for companies like The Gap, Victoria's Secrets, and each one of these are body parts. These body parts are identified by limbs and torsos, heads, and it's an injection molding process that shoots polyurethane foam into a mold. The molds are identified with an RFID tag, and like the pay at the pump, we attached an RFID reader that was attached to their PLC to identify that mold and then shoot the polyurethane that's necessary for each specific mold into the body of that mold. It did two things. It identified how much material, it prevented any injury to employees, and it also gave them a higher quality of parts. I'll show you some of the pictures here. We talked about 13.56 megahertz not being as metal friendly, and this is a good example where we could have possibly attached a metal mountable 13.56 megahertz tag to the mold. However, we found that 125 kilohertz was a better suited technology for this environment. This was the tag that was utilized, and we'll talk about this in a little bit, but you'll see that it's flat and long. And inside of this particular tag, it's made to mount directly onto metal and be able to be read as it's mounted onto a metal surface. We'll talk about the different types of antennas that are inside of the tag as we get further along in the presentation. However, this tag was mounted with what's called a ferrite core. In the ferrite core, it allows for that tag to be read from the narrow surfaces. Let's see if I can show you this. It would be reading pointing right or left rather than reading from the flat surface on the top. This was the antenna and the reader that was used. This is what we call our smart antennas. This is available in various sizes and shapes and various heads. This combines the reader electronics as well as the antenna electronics all into the antenna housing. Of this technology, we're able to network up to 32 devices back to a single PLC. And again, this is what we refer to as our smart antennas. The next slide shows this actually in progress, where you can see the antenna, the smart antenna, attached to their injection molding machine, and the tag is attached onto the mold. This is one mold. There's another mold over here with another tag on it. And this is a giant spinning device. So after this urethane is injected into the mold, it goes through a spinning procedure, and then it's the mold is created. The next slide will show some of the mannequins as they're finished. So here you can see heads, arms, body parts, and the operator on this particular device. Another application in mold identification is the longevity of that particular mold before it needs to be processed for any type of cleaning or maintenance. And of that, again, we utilized a tag on the mold and a reader attached to their controls. And in this particular process, it was identified X number of times before that mold needed to be pulled off and go to maintenance. Again, this was 125 kilohertz that was utilized based on the time that it was implemented. So today, we might look at using UHF, but it hadn't been commercialized at that time. This particular installation that we'll show you goes back to the early 1990s. So that's 30 years ago that this was installed. And we still support this customer in their application, in their installation. Over the past 30 years, RFID Inc. has never discontinued a product. So we'll continue to focus on always having a product that is consumed and make that available for those customers. Moments ago, we talked about the difference between an antenna of the tag. So here you can see this ferrite core on the top of this particular tag. And with this, you would have your RF field off to the right or left. The large copper coil that you see is referred to as a planar antenna. And with the field that's generated from the planar antenna, that would be a top-facing field. So that would give you the ability of having your antenna or your smart antenna pointing towards the top of the tag rather than the ends of the tag if it were with the ferrite core. In this particular case, the customer utilized what's called the planar antenna. They used the same smart antenna as what we showed earlier with the mannequin application. And this is the process. So as you can see, this is an RFID tag that's attached to the mold. And as it went past this reader, it kept track of the number of cycles that that mold went through. It's a close-up view. These are disposable razors that are being manufactured. We also were involved with engine blocks. And we did this with tags that were high temperature, low frequency tags at the time. Today, we now have UHF tags that are available at 400 degrees C, and in prototyping right now is 550 degrees C. So in this particular application, we were just tracking their molds through the process. And it was very rough, dirty environment. This Chrysler engine blocks going back years ago. This was installed again at 125 kilohertz. Read range was pretty short, but now it's moved to UHF and they have about 7 meters of read distance. These are the differences in the tags that are utilized. The tags on the left are low frequency tags, and this is spec to 230 degrees C. The tags on the right are FR4 tags, they're UHF, and they're spec to 200 degrees C. Some of our other high temperature tags, like I say, can go up to 400 degrees C, as well as up to 550 C. The readers that were utilized in this application are shown on the left, and it was an all-in-one reader with an antenna. And then today we would utilize our UHF reader. Again, it's all-in-one. The antenna sits here on the left-hand side, and the reader is outfitted in the back. This was the application. The reader's not visible. It's up here in this box. or the tag's not visible. The reader's contained up here in this box. And it was identified as it moved through their process. It was a very harsh process, like I said. These are sandblasted or sand cast blocks that were produced for aluminum engines. Did a similar project for another manufacturer, same type of thing, utilizing low frequency. It's kind of a different application. When you think of exhaust pipes, typically what happens is that pipes are bent to a specific part or a specific car. And so when the manufacturer of the pipes needs to put together an order for pipes, he'll have a long piece of pipe, and that pipe will be bent at various areas to accommodate whatever vehicle. When they do that, they use what's called these soft copper donuts on the end of their bender arm, the mandrel that is extruded into the pipe for it to be bent in certain areas. So these copper donuts sometimes break off. And when that happens, originally the operators weren't notified. The other thing happens is that if that particular exhaust pipe goes off to General Motors and they're not able to start the car, then there's some substantial losses on a daily and hourly basis. So what we did is we put RFID tags on the end of the copper donuts to identify where and which pipe that last copper donut might be found. And so it was really a quality issue. Again, we use low frequency technologies for this, just to verify which tool is in place, the number of donuts that are applied, and verify if any is broken off, and identify the pipe so that another end donut could be placed onto the pipe. The low frequency tags were utilized in this application, and these were the two types that were used. Both of these are made for very precise reading, and you'll see in the next slide the antenna, the smart antenna reader that was utilized. When you look at this and you look at how they were presented, you think, well, they're in the wrong orientation. But in fact, the coils match up to one another, giving them the correct orientation when the mandrel arm was presented to the reader, the smart antenna. Here you can see a slide. This is with the first tag, the white tag that we showed. And up here on top is the smart antenna, the 5120 smart antenna. And from here to here, the distance was about 6 inches. And that would allow that tag to be read. And in the event that this particular donut was broken off, the machine would shut down and the operator would know that the last pipe that was bent is defective because it has this donut lodged inside of the pipe. Very similar application, but here we have closer proximity due to the size of the tag. So this tag here is 22 millimeters, and this is a 30 millimeter head or smart antenna that's housed inside of a piece of UHMW. And that gives the same orientation, side-by-side orientation, to identify that particular donut on the mandrel arm. CNC machines, a lot of you are all familiar with that. But typically what happens is with a CNC machine, you're looking to identify one piece of metal or plastic or Teflon to a specific cutting tool. And so by identifying that particular tool in your process, it gives you the ability of organizing your racks as well as selecting the right tool for the right job. We do this quite a bit, and it removes any human process and creates an automated process. The RFID tags are typically very small, and they're surface mounted, they're subsurface mounted. Read ranges vary from short, almost contact to an inch, or up to several inches, or even feet if we use UHF metal mountable embeddable tags. These are some of the examples of the tags that we're utilizing for both low frequency and ultra high frequency for this specific application. So these little tags here kind of indicate the size. These are low frequency tags, and they're made to, they're manufactured to mount into metal. Each one of them have what's called a ferrite core, and we talked about that earlier. The same thing is true with this class ampule. Inside, you can see the copper windings as well as the ferrite core inside of the ampule. The same ampule is mounted inside of this coffin tag, as well as it's manufactured here with copper coil windings around a ferrite core. The UHF tags shown here on the left side of the page with the ruler, they have a higher bandwidth of 915 megahertz, and mounted into metal, these small tags achieve a read distance 3 to 6 inches, depending upon the depth of mounting and any surface area around it, all the way into getting into feet. But because CNC machines are very precise and controlled, typically you want to read one tag at a time. This is the UHF antenna that's being used. This is the low frequency smart antenna that's being used. This here is 16 millimeter in diameter. And you'll see in the next slide is how that's being implemented. This is the antenna mounted onto an arm. Tag is mounted onto the tool, and it's identified as it goes into any process, whatever the next process is. And that's the presentation from RFID Incorporated. I appreciate your time. I see that there's some questions out there. I'll let it go to Tim here, and I'll take a look at the chat questions.
John, I'll ask you a question. You mentioned LF and UHF. Do you see the mid-range HF in those type of applications?
Not really too much, Rob. Typically what you'll see is that HF has about the same limitations as what we have with LF. When you mount an HF tag onto metal, typically you're using a larger surface area and achieving the same read distance as what you would with LF. When you get into any sub-material mounting, HF doesn't work. So we have to look at using either a lower frequency or using UHF for any sub-material mounting.
You know, I've always gone to you guys on these types of jobs to help select which one is better. Is that balance between LF and UHF been pretty constant, or have you seen a shift over the last couple of years?
We're seeing both. So it really just depends on the application. Again, what happens with LF is that it's very precise. So you're a very controlled process and application. When you look at UHF, sometime, somewhere, you're going to get an errant read, and you're going to pick up a tag that's going to be not specific to what it is that you want to see. Now, this can be overcome through software by identifying which tag that you want to read multiple times. And that's typically what happens. Because an errant read, you might get a tag that's energized once a week, and it reports back to your reader. And you don't want that interfering with your process. So it really depends on the application, Rob, but a lot of times we're seeing transition over to UHF because we can get a greater read distance with a small antenna and a small tag.
And I assume from a PLC integration point of view, it doesn't matter. It's a control, it's a reader control regardless.
That's correct. We support all of the field bus protocols with both LF as well as UHF.
Thank you.
Thanks for your questions.
Any other questions on John's portion before I jump into my side of things? All right.
I have a question from Manuel, and he asks, do you consider then use a linear antenna and UHF solution will reduce the trouble to read multiple tags? If you have a tag that is mounted horizontally and you have a antenna that is horizontally polarized, you will maximize your read distance. So if in fact you use a circular polarized antenna or a vertical polarized antenna with a tag that is mounted horizontally, you will shorten your read distance by 1/2. The only other way to reduce multiple reads is to use a lesser gain antenna. So the smaller the gain and the orientation of the tag will prevent multiple reads outside of the reading area. Manuel, I hope that answers your question. I have another question. What is the comparison of the different frequency tags in terms of cost? Typically, an LF tag will cost more than a UHF tag. So it depends on the characteristics of the tag, because we have some high temperature, ultra high temperature tags that are in the $40 range. So in that case, we have high temperature tags that cost more than low frequency high temperature tags. So it really depends. But as a general rule, LF is going to be more than UHF. Conrad has a question. What is the comparison of the different frequencies in terms of cost? I guess I just answered that one.
Yep. Any other questions for John before I start?
I think you're good to go, Tim. I'm going to just go ahead and mute.
Sounds good. So John has given us some really great detailed examples of using RFID tags to track the molding and the number of hits on the molding and everything else. What I'm going to talk about is using the Industrial Internet of Things and some software that we have there, and machine learning to drive performance improvements as well. So in my example that I'm going to go through here, we had a customer that was doing grinding and they were using a grinding wheel. And the opportunity was that, if they left the grinding wheels on too long, they would produce bad quality parts. If they took the grinding wheels off too soon, then they're spending too much money on grinding wheels. And so they erred on the side of caution typically. So they would take those grinding wheels off before they would, start producing bad parts because they didn't see the quality issues typically for several operations downstream. So they could produce a lot of bad parts before they would see it. And so the current state is to replace the wheels after producing a set number of units. And this is the initial scope for this is across 4 different grinding operations. And the solution that we put in place is to automatically collect detailed tag and process variable information from the PLCs of the grinding machines. And as a first pass, we were using individual metrics to look at boundaries and alerts and so forth for when the tool should be changed, and using visual controls and alerts to notify personnel. And over the long term, what we're doing is we're using the machine learning algorithm to monitor multiple tags to do predictive analysis on when to make those tooling changes. So some additional things that we're getting as we do that. Right now, they're not really doing a whole lot of detailed downtime reporting. It's just when the operator has a really big downtime event, they'll go and they'll enter that into the SAP shop floor application. And there's no capturing of any minor stops or micro stops. And the accuracy of the data is, definitely a concern. So as we do this, we're going to automate a lot of different data collection other than just for the tooling itself. We're going to be looking at uptime and downtime on the machines. We're going to be looking at, being able to do some predictive quality as well as some of the predictive tooling and so forth. And we'll be able to, implement some visual factory techniques so that we can alert people when, there's downtime on those machines going on and so forth. So we did a proof of concept back pre-pandemic, and we were able to identify, what things looked like when, a tool was approaching the end of its life, and, the additional variants that we would see when the tool was known to be bad. We could definitely identify, those things. And then for a new wheel that was going on there, we could see that it was operating within, a much tighter tolerance. And we had occasional spikes as, different things were going on, but those were one-off. So if you looked at, having multiple readings outside of that band, you could definitely identify when things were going bad. The current state in the application is we can see, as this tool was approaching its end of life, we started seeing, we've set the tolerance to be, at a point where the amplitude and the variability of that is such that when it reaches a certain boundary, we recommend the tooling change. And then we can see going from that down to the new tool. And after, a little bit of a break-in period, you can see where it really hones in on, a certain level of performance. And, we're also, again, capturing running, not running, and, a lot of different information about the machine as well. So quite a bit of information there. And we're really able to now optimize when those tools should be changed out. And, we're looking to do, even better once we start doing the predictive model based on multiple metrics. But even just looking at the torque power reading has been absolutely tremendous in terms of being predictive on when we should be changing those tools. So when we look at the things that, John talked about, when, the things that, we did within this particular scenario, and we look at, what is the payback for these types of investments? Certainly, looking at the tooling and maintenance costs themselves, the customer in my example was spending, hundreds of thousands of dollars a year on tooling, refurbishment, and replacement. And being able to reduce those costs was certainly a key part of the investment. Looking at the total cost of quality, and being able to reduce scrap and rework, how much testing has to be done, escapes, out to the customer and so forth, and then just handling of all those parts. Being able to reduce the labor cost per piece by identifying and eliminating waste and improving standard work. What we found was that the profile of when one operator was running that process versus a different operator was extremely different. And by really identifying what they were doing differently as they were running the process and creating that detailed standard work, we were able to take the best things that each operator was doing and combine those into how to run the process. Throughput in sales by reducing the amount of downtime, reducing the changeovers and so forth. We were really able to reduce or improve the amount of throughput that the plant was able to achieve. We haven't seen an impact in warranty yet, but certainly the risk is mitigated there because we have a much higher degree of confidence that we're not going to be producing bad parts. Before, when they let the wheel run to 50,000 units, if you had a bad wheel, you were going to be producing bad parts by the time that you hit 50,000. And so there was a much greater risk of having those escapes out to the field. And then, additional minor impacts in terms of WIP cost reduction, expediting costs, and so forth. And so there is a tremendous amount of payback potential for making these types of investments, whether it's in the IIoT and machine learning space, or whether it's in the RFID space that we were talking about earlier. And honestly, those can be combined very easily, where that RFID tag is feeding into that Internet of Things software, and is tracking the tooling within there, as well as the information coming from the PLC of the machine. That way you can get detailed information on the hits and so forth. I've got another customer that's actually doing that, where they have a large scale press, and they have very complicated die that they're using within that press that has multiple pieces to it. And they're actually looking at tracking the individual components within that die set to be able to track the hits on each component within there, because as those go into or come off of the machine, go back to the inventory, there's maintenance done on those, and they're kind of disassembled, reassembled, and each die set will contain different components each time that it goes to the machine. And so being able to track those in more detail will allow them to really see and optimize the maintenance that they're doing on each one of those. Any questions from my example, and being able to really look at the value of doing these things? Well, with that then, any other questions for John that people have thought of?
I have a question for both of you guys. Since I come to this from an integration point of view, in some instances, the PLC has the logic to be tracking the tool, and we're simply integrating the RFID to the PLC. In other cases, we're looking at preventative maintenance, as you've laid out, and other functions that require standalone software. And of course, you have a hybrid where you're feeding the PLC control, but you're also doing some other tracking with the IoT software or some other form of software. I'm curious from John and Tim, rough ratio of the integration work you've seen, how much is directly into the PLC versus other type of software controlling the reader.
From my point of view, I more often work with taking that information from the RFID reader into the external software. But I've certainly seen applications of it where it goes into the PLC and then we just integrate to the PLC to get that data. I think it really depends on the particular use case as to which of those is more appropriate or easier. John, do you have thoughts on that?
I think he's still on mute. We'll let that remain a mystery.
We will. All right. Well, thank you everyone for attending. And thank you, Manuel, for the comment there. And you're welcome. And we will follow up with everyone that attended. The information will be posted, the recording of the presentation and the deck will be posted to my website at www.visualdecisions.com. And I'll probably have that up sometime late tomorrow. So if you check Thursday morning, everything should be available. With that, thank you all and have a great day.
Thanks, Tim. Thanks, Rob. And again, thank you all for your interest and participation.